Hello there! This is Tierney from Monroe Community College, and we're going to be talking about aqueous reactions in this video. And we're going to specifically talk about how we represent them. There are a few different ways in which we can write aqueous reactions, and we're going to be talking about 3 different ways in which we represent them. So in the last video, if you recall, we got a little meta and we watched a video within a video. And we watched this reaction right here. Sodium iodide plus mercury chloride, and that gave us sodium chloride and mercury iodide. And if you recall, the orange solid that was produced, we called that the precipitate. This type of reaction is what we're used to looking at when we think of a chemical reaction. This is called a molecular equation. A molecular equation shows all reactants and products as if they are intact, not dissociated. And dissociated, we're going to talk about what that means, but it means that it's broken up, and we know that ionic compounds break up into their ions when they're in solution. Now, if we were to look at what's actually going on in this reaction, when we add these 2 compounds to water, before we even mix them, they're already broken apart. They're dissociated into their ions. So if we look at the sodium iodide, the sodium ions and the iodide ions have already broken apart, they're dissociated, and they're floating around in the solution. Same with the mercury and chloride ions in mercury chloride. This is represented by our next type of equation, the total ionic equation. This shows what's actually going on before the reaction occurs. And how we write that is we show that all soluble ionic compounds have dissociated into ions. So what we think about is if you see an aqueous substance, you're going to quote-unquote break it up. All gas, solid, and liquid substances stay together. Now, aqueous substances are all going to break up except for there is one small exception to this rule, weak acids, and we're going to talk about that later. So if we take a look at this example problem that we've been looking at, the molecular equation we already wrote. Now we're going to write the total ionic equation. And we're going to look at each individual substance and determine whether it will dissociate into ions. So first we're going to look at the sodium iodide. We know that the sodium iodide is an aqueous ionic solution, so we're going to write it as the ions that have broken up. So we are going to write that for 2 sodium iodides, we have 2 sodium ions and 2 iodide ions. I want you to notice that the 2 has carried through to both ions. Same with the aqueous attachment. You also need to include the charge. For sodium, it's the sodium plus. For iodide, it's the I minus. Same with the HgCl2, or mercury chloride. We're also going to break that up because it is also an aqueous ionic compound. So we're going to break it up into its mercury and chloride ions. Notice that the 2 from the chloride right here, that gets turned into a large 2 because those 2 chlorines are actually going to break up. So if we go back, we see that these 2 chloride ions are not attached. They are separated. So we need to denote that as a big 2 instead of a little 2. On the product side, we need to determine what will break up and what will not break up. We know that sodium chloride is aqueous, so it is going to be made up of sodium ions and chloride ions that are separate from each other. Now the precipitate is a solid, and we see above that all gaseous, solid, and liquid substances stay together. So we write that as a solid, and we keep it together. So this is what we have so far. We've mixed our solutions together, and now we have produced a solid. Our last way of representing this reaction is called a net ionic equation, and a net ionic equation basically just tells us what has happened. In this case, we have produced a solid, mercury iodide. Our sodium ions and our chloride ions, they have stayed ions throughout the entire process. They're just watching, they're not doing anything. It's these mercury and these iodide ions that have come together to form a solid. And the net ionic equation, that focuses on what has actually happened. So in order to write a net ionic equation, we do not include something called spectator ions. Spectator ions are the ones that have the same charge and state of matter on both sides of your equation. Now if we look at our picture, those are the ones that don't change at all. So chloride starts as a chloride ion, ends as a chloride ion. It is a spectator ion. So in our net ionic equation, let me show you what we have so far. We have our molecular equation and our total ionic equation. We need to determine first, in our total ionic equation, who are the spectator ions. So I want you to look at our total ionic equation and identify which species are exactly the same on both sides. They need to have the same charge and the same state of matter. So we see that 2Na plus aqueous is exactly the same on both sides. Let's circle those. Those are spectator ions. There's one more spectator ion for us to circle. That is the chlorides. Those are the same on both sides. So in order to write our net ionic equation, we're going to write everything that we haven't circled from our total ionic equation. So we have our iodide ions plus our mercury ion, and that gives us our product, our precipitate, mercury iodide. So now I would like you to give this a try. Here's another example. I want you to write the total ionic equation as well as the net ionic equation, and then I'll show you the answer after you press play. So press pause right now, give it a try, and then press play when you're ready for the answer. So here's our total ionic equation. Take a look at that and see if you got it correct. Make sure you look at every little individual thing to correct yourself. Did you get the charge right? Did you get the coefficient right? There's a lot of little details here. Now in order to write our net ionic equation, let's identify the spectator ions. Magnesium ion, looks like that is a spectator ion. How about our bromides? Yes, that is a spectator ion. The sodiums, yes, those are spectator ions. And how about our nitrates? Uh-oh, we circled everything. What does that mean? This was kind of a trick question, wasn't it? It means we had no net reaction. Recall that when you produce two aqueous products from two aqueous products, that means nothing has actually happened. You just have a bunch of ions floating around, no reaction occurred. So I want you to try one more. This is the your turn problem. So I want you to come to class ready to discuss your answer. I want you to write the total ionic equation as well as the net ionic equation for this molecular equation. I'll see you in class.